Check out this really simple demonstration. This person takes a wire and connects it to a battery. Current is flowing through the wire, and then he brings the wire near a compass. Notice how the compass needle deflects or moves when this current is brought near to it. This is a really fundamental phenomenon. In chapter 28, we talked about the force acting on a charge or current exposed to a magnetic field. In chapter 29, we focus on the magnetic fields created by a moving charge or current. It seems that a moving charge creates its own magnetic field. It's this created magnetic field that's interacting with the compass needle and causing it to move. Magnetic fields are critically important. They explain a lot of natural phenomena, and they have a ton of practical applications because they store energy and they exert a force. Nature says a moving charge creates its own magnetic field. Let's examine this odd-shaped wire. Our job is to figure out the strength and direction of the magnetic field created by the current flowing through this wire, specifically at point P and point P prime. We see the direction of the conventional current. We're going to take an infinitesimally small segment of wire. The length of this tiny segment is ds. The vector ds has a magnitude corresponding to the length of this wire, and the direction is the same as the current direction. This tiny current element is located a distance r away from P and r away from P prime. This unit vector r hat is a unit vector specifying the direction from the current element to the point P or P prime. Theta is the angle between that r hat directional vector and the ds vector, and I should mention at point P you see a green dot. That means the magnetic field at point P is coming out of the page. At point P prime you see an X. That means the magnetic field vector, which we're calling dBn, is going into the page at this point. Box 2 summarizes everything I just said. Box 3 shows you what was found. When a current flows through a wire, a magnetic field is created. This magnetic field has a particular orientation with respect to the ds vector and the r hat vector. The strength of this magnetic field is inversely proportional to the square of the distance between the point you're investigating and the source of the magnetic field. This is yet another inverse square law. The strength of the magnetic field is directly proportional to the current and to the length of the element. So a really strong magnetic field gets produced by a very large current, and the longer the current element, the stronger the magnetic field. This last bullet point shows that there's a dependency on the orientation between the point you're investigating and the direction of the current. So if we put everything together, we get this expression, which conveys the magnitude and direction of the magnetic field produced by an infinitesimally small current element at some point P, a distance r away from that element. This is our fundamental building block. Pretty much everything that follows in this chapter is based on this expression. We introduce a new constant. Mu naught is a constant called the permeability of free space. Now that we know everything about a current element, we can integrate to get the net effect of a series of current elements, also known as a wire. Although technically speaking, current does not need to flow through a wire. The bottom line is we integrate to add the cumulative effect of a number of current elements. This is known as the Biot-Savart Law. As noted here, the Biot-Savart Law is also used in aerodynamics to analyze vortexes. Okay, now that you're completely familiar with the basic building block, let's examine some special cases. It's time to derive the magnetic field surrounding a thin, straight conductor. Let's look at a Fallstad simulation. You're looking at a long, straight, current-carrying conductor. Here are the magnetic field lines surrounding this long, straight, current-carrying conductor. It looks like a whole bunch of concentric circles that get stronger as you go closer to the wire. This is what it looks like if I start the animation in 3 dimensions. This is what it looks like if I display magnetic field vectors, which are everywhere tangent to magnetic field lines. So again, field vectors and field lines. We're going to start here with our basic building block, Biot-Savart Law. Bullet number 2 is a reminder. As usual, the goal is to formulate an integral that captures the pertinent geometry and material properties and correlates them in a solvable integral. To the maximum extent possible, capture variables that are physically measurable in your integral. Let me spend some time on box 1, which asks the question, what's the direction of the vector ds crossed with the r hat vector? The answer is k hat. By now, you really have to have a solid understanding of how to do cross products. You have to be able to see that if I do A cross B, I use the right-hand rule to curl vector A into vector B, producing this result. Go ahead and fight your way through boxes 2 through 9. There's a lot going on. You have trigonometric identities, cross products, and geometry stuff. Remember, really mastering these derivations makes you a better problem solver. It makes you more creative and more insightful. Follow up if anything you see doesn't make sense. Boxes 10 through 16 is more of the same. Lots of intricate steps and clever substitutions. Now we have to use integral calculus. And in box 16, we finally get our result. The magnitude of the magnetic field produced by a current carrying straight line wire equals mu naught times I divided by 2 pi A. I is the source current being carried through this straight line conductor. A is the distance from that straight line conductor to the point you're interested in. That's where Probert is standing. This shows the strength of the magnetic field, but we also have to worry about the direction of the magnetic field. Here's a good overview visual from the Hyperphysics website. You take your right hand, you grab the wire, your thumb points in the direction of the current flow, and your curled fingers show the direction of the magnetic field. In this case, only a few magnetic field lines are shown, and those few that are shown are limited to a single plane. Remember, in reality, the magnetic field lines extend radially outward from that wire and extend along the entire length of that wire, not just limited to a single plane. This box shows us the similarity between the result we gained for the electric field at a point at some distance r away from a current carrying wire. Check out this classic demonstration showing compasses surrounding a current carrying wire.
But the standard and traditional way of showing magnetic fields is with a compass. I've got a wire, I'm going to put electricity through that wire, and I've got it surrounded by compasses. Compass points towards a magnetic field. And if you were to bring a strong magnet near it, they would point towards it. So I got a little strong magnet in my hand, you can see they point towards it. And an interesting phenomenon takes place. I'll get it lined up. When we put electricity through a wire, it creates a magnetic field. And the magnetic field is just going around that wire. And if you wrap the fingers of your hand, they go in the direction of the magnetic field.
Okay, let's graduate from looking at what happens with a current carrying straight wire to finding the magnitude and direction of the magnetic field at that point P indicated here due to a constant current flowing in a circular loop. Remember, this current could be flowing with or without a wire. Same approach. We identify an infinitesimally small element of this loop. We indicate all the directional vectors. The magnitude of this ds vector corresponds to the size of the infinitesimally small current element. The direction is the same as the current. This unit vector r hat is a directional vector which points from the current element to the point we're interested, labeled point P, and r is the distance from this current carrying element to the point. Let's look at Falstad. Here's a constant current carrying wire loop. This is what I get when I turn on the magnetic field lines. If I run the animation, you can see the three-dimensional properties of these field lines. All of these result from using the right-hand rule at every current element along the loop. So if we go back to our basic drawing and again limit ourselves to an examination of a single infinitesimally small current element that you see here, we can see how we get the resulting magnetic field line here. Here's an important insight. If I decompose this magnetic field vector at point P into its x, y, and z components, hopefully you can see how all of the y and all of the the Z components cancel. Make sure you spend a lot of time considering this and make sure you come to the same conclusion. Okay, we're going to use the same exact approach. We start with the Biot-Savart Law for an individual current element. Carefully scrutinize boxes 1 through 6. In box 3, again, make sure you agree that all of the Y and all of the Z magnetic field components cancel, leaving only the X component. Boxes 4, 5, and 6 employ a lot of trigonometry, geometry, cross product rules, and integral calculus. Lots of stuff to study here. In box 7, you evaluate the integral and get a result. Box 8 is a special case, so it's kind of a special case of a special case, but it's the case that we care about almost exclusively. What's going on with the magnetic field at the very center of the loop? Go back to box 7, set x equal to 0, because again, we're looking at what happens at the center of that planar loop, and that's how you get the result in box 8. This is the magnetic field of a constant current circular loop at its dead center. Let's take a look at a simple demonstration. Here you see a stack of single loops. We're using a stack just so you can more clearly see the effect. This loop is embedded in a clear piece of plexiglass. It's connected to a battery. Current flows through the loop, creates a magnetic field, and causes these iron filings, which were sprinkled on, to align along the magnetic field lines. Okay, let's move on to the next special case. You're looking at two straight parallel conductors. Each of them carries a constant current. The current flowing through wire A creates a magnetic field, as we've discussed. Wire B, therefore, is exposed to this magnetic field that is created by the current flowing through wire A. Now we revert back to chapter 28, where we studied what happens to a current when it's exposed to an external magnetic field. This is a pretty challenging application of two different right-hand rules. You use what I call the pop can right-hand rule to find out what's going on with the magnetic field created around wire A and also encountering wire B. For wire B, you use what I call the flat hand right-hand rule, which I've discussed. Your thumb points in the direction of the current flowing through wire B. Your fingers are aligned with the direction of the magnetic field existing along wire B due to wire A, and your palm is pointing in the direction of the magnetic force acting on wire B due to the magnetic field created by the current flowing through wire A. Phew. Okay, let's look at box 2. The current flowing through wire A creates a magnetic field. There's the expression. Box 3 is a really important box. Make sure you can see that if you use the right-hand rule for wire A to determine the shape and direction of the magnetic field lines, you can see how the magnetic field at the wire B due to wire A is pointed straight down. That's a really important step. Don't gloss over it. Box 4 also comes from chapter 28. We've seen this before and used it a lot. In fact, you derived it. F equals IL cross B. This is the magnetic force exerted on wire B due to the magnetic field created by wire A. It is absolutely critical to commit to subscripts in this case. F underscore BA means the force exerted on wire B due to wire A. Always use that convention. On what, from what. It's I subscript B because it's the current flowing through wire B that is subjected to the force. It's L subscript B because we are again examining the force exerted on wire B, but it's B subscript A because it's the magnetic field created by the current flowing through wire A that's acting on wire B. Tricky. Boxes 5 through 8. Box 5, we switch from cross product form to magnitude angle form for magnitude. Box 6, make sure you agree that theta equals 90 degrees, which is the angle between vector L subscript B and vector B subscript A. Follow the operations shown in boxes 7 and 8, which culminate in this expression. This is the force exerted on wire B due to a magnetic field created by wire A that's parallel with it. That's the caveat. These are two constant current carrying parallel wires. Box number 9 is just another double check. Are you sure that you understand how the force acting on wire B is pointing directly to wire A? This is a job for the right-hand rule. Box 10 is a simple rule that falls out from all of this. Parallel currents attract each other and anti-parallel currents repel each other. Let's check out this demonstration from MIT. Box 11 summarizes the operation of something called a railgun. I'm including it here because it includes capacitors, which was chapter 25, along with magnetic forces, which was chapter 28, and the creation of magnetic fields, which is chapter 29. Check it out. Next section, Ampere's law. We're going to derive what you see here on the screen. A closed loop, also known as a contour integral of B dot ds equals mu naught times the enclosed current. This might remind you a bit of Gauss's law that we studied in chapter 23. Ampere's law is a cornerstone of electromagnetics and actually makes a lot of situations easier to analyze. Box 1. Once again, we take an infinitesimally small differential element. We figure out what's happening with that element and integrate to get the cumulative effect. Let's look at a really small current element, label it, and apply all of the directional vectors. And remember that we solved the situation using Biot-Savart. We can figure out the strength of the magnetic field produced by this current carrying straight wire at that point P. You can use your pop can right-hand rule, or you can cross vector ds here into vector r hat and get the same result. The magnetic field at point P is coming out of the page towards you, also known as the plus k hat direction. Box 4 wants you to imagine looking at this wire straight on. You're looking down that wire so that the current is literally coming up out of the page towards your eyeball. Make sure you satisfy yourself that what you're looking at here in box 4 is exactly what you were looking at here in this diagram, just from a different point of view. Box 5 says, okay, now that you've figured this out for that point, walk around this wire maintaining a constant distance a away from it and keep drawing magnetic field vectors all along the way. This is what you would get. Box 6 says, okay, take what you have there in box 5 and break it up into teeny tiny differential line segments. Each line segment is denoted by vector ds, where the magnitude of ds is the magnitude of the differential line segment, and the direction of that vector ds is always parallel to the magnetic field vector shown. Box 7 says, okay, let's add up all of those dot products. Let's take the dot product of vector B and vector ds and add them all up along that entire contour or loop. Box 8, let's represent the same thing using magnitude angle form. Box 9, satisfy yourself that the angle between that vector B and the vector ds is theta equals 0. They are parallel. Box 10, this is what we get because cosine of 0 equals 1. Box 11, the magnetic field strength is constant because we're taking measurements at a distance a from that current carrying straight wire. We're doing that as we encircle that wire, so it is again a constant distance, which means a constant magnetic field strength. Box 12, the integral of ds is s, and s represents arc length, which in this circumstance is circumference, 2 pi a. Box 13, we already figured out the magnetic field strength at some point in the vicinity of a current carrying straight wire. We use the Biot-Savart law to get mu naught I over 2 pi a and go to box 14. So let's plug that in, simplify, and we end up with box 14. This is Ampere's law. The contour integral of vector B dot vector ds equals mu naught times the amount of current enclosed by that Amperian loop. Okay, let's derive the magnetic field outside a long straight wire. This time though, let's use Ampere's law. We need to find the magnetic field direction and strength at some distance r away from the center of this wire. You're looking at this wire head on. The wire is perpendicular to the page. In this case, the current flowing through the wire is coming up out of the page towards your eyeball because it's indicated by a black dot rather than a black X. The Amperian loop refers to an imaginary loop that is sized to coincide with the point that we're interested in investigating. There's my ds vector and its associated magnetic field vector B. Again, theta equals 0. There it is. Box 1, we start with Ampere's law. Box 2, same thing, only use magnitude angle form. Box 3, the The magnetic field is constant because at every point surrounding this wire, probert is remaining on that Amperian loop, which has a radius of r. Probert is always a distance r away from the current, which means the magnetic field will remain constant all along that Amperian surface. Box 4, you can see the angle between the ds vector and the b vector is 0. Box 5, let's update the integral in box 2. Box 6, the integral of ds is s, and s equals 2 pi r, the circumference, which is the path length of this Amperian loop. We simplify and end up with box 7. We used Biot-Savart previously to figure this out, but using Ampere's law does the same thing, only it's much easier. Just like Gauss's law handled simple geometries, Ampere's law, the way we apply it at this level, is restricted to simple loop geometries. Last section, solenoids. We just investigated what's happening with a current-carrying circular loop of wire. Here we take a really long wire and wrap it into multiple loops and line them up as you see here. At the top, you see current coming out of a loop, winding around, and then at the bottom, flowing into the page away from you. That's why at the top we see a black dot, and at the bottom we see a black X. If you applied the right-hand rule at every point along this coil of wire, you would get the magnetic field lines shown here. You can see that the interior magnetic field is relatively uniform and strong, while the external magnetic field is pretty weak. In a perfect solenoid, the internal magnetic field would be perfectly uniform and the external magnetic field would be non-existent. Solenoids are in many ways the magnetic version of capacitors. Capacitors store energy in the electric field between their plates, and a solenoid stores magnetic energy within its coils. So a solenoid is an energy storage device, and we can also tap into that energy to do work. Check out this solenoid demonstration.
We'll visualize that magnetic field using these black iron filings. When I put a current through this coil, so I'm just going to hold this button down for half a second or so I don't burn out these wires. And you can see definitely the alignment of the particles coming through the center of the solenoid, starting to come back around the outside. The field is much weaker along the outside.
Check out this Fallstad simulation of a solenoid. Note the direction of the current flowing through the wire. It's using particle velocity to convey a sense of the magnetic field orientation and strength. Once again, inside things are pretty strong and uniform, outside pretty weak. Here's what it looks like when I display the magnetic field vectors. Now I'm flying around it in 3 dimensions. Here's what happens when I increase the winding density, also known as the number of loops per unit length. Now I'm displaying the magnetic field vectors, which are everywhere tangent to the magnetic field lines. I've increased the length of this solenoid, and this gives you a good visual. Look at how uniform the magnetic field is inside the solenoid. Check out this solenoid actuator. Actuators are devices that make parts move. Actuators control the motion of robots and countless other mechanical devices, ranging from artificial limbs to computer hard disk controllers. Check out this explanation of solenoid valves.
Solenoid valves are used to convert electrical energy into mechanical energy. Solenoid valves have quite a distinctive look about them. As you would expect, they have the valve body, but on the top they have a block which will have some cables coming out once the valve is installed. This top part is the solenoid and the bottom part is the valve, therefore making a solenoid valve. Here's a small real-world solenoid valve. Now these valves do come in a variety of shapes and sizes. Why do we use solenoid valves? Well, these valves allow engineers to autonomously and remotely control the flow of fluid within a system. This fluid can be a liquid or a gas, for example water, air, natural gas, oil, steam, refrigerant, etc. The list goes on and on. The solenoid coil on the top is used to operate the valve by passing an electrical current through it to create an electromagnetic field and operate the valve. This means if it is connected to a controller, it can be operated autonomously and remotely by a computer without the need for engineers to physically run around opening and closing valves. This allows systems to run much more efficiently and safely. So where do we use or find solenoid valves? The short answer is everywhere. Solenoid valves can be found in everything from washing machines up to space rockets, although we're going to focus on the industrial and HVAC applications for this video.
Okay, the goal is to find the magnetic field at the very center of the solenoid that you see there, labeled P subscript 1. The following analysis assumes an ideal solenoid. That means there is no magnetic field outside the solenoid, which is relatively true if the length is quite a bit larger than the diameter. Box 3, start with Ampere's law. Box 4, draw the Amperian loop. I'm going to draw this rectangle with the vertices A, B, C, and D. You can see that the current is coming out towards you from the top loops of the solenoid, hence the blue dot. They're wrapping around and then going down into the screen away from you at the bottom, hence the blue X's. Box 5, I'm breaking this integral into 4 pieces, one for each side of my Amperian loop. I'm integrating from A to B and then from B to C, C to D, and from D back to A. Box 6, you can see that 3 out of the 4 integrals equals 0. For the integral from A to B, theta equals 0, cosine of 0 is 1, theta is 90 for the segment BC, so that equals 0. For the segment C to D, there is no magnetic field, so it makes no contribution. That's why that integral equals 0. And finally, from D to A, theta equals 90 or 270, cosine of 90 or cosine of 270 equals 0, hence that term drops out. So this is our result in box 6, B times H. That's the left side of Gauss's law. The right side is mu naught times the amount of enclosed current. Let's look at that in box 7. Within the Amperian loop, I'm capturing some number of turns per some unit length. If I solve for the number of terms, I'm using the unit length equaling to H, which is given in the visual. So box 7 is giving me the number of turns enclosed by my Amperian loop. Box number 8, I know the number of turns that I have enclosed by my Amperian loop. I multiply that by I, the current through each one of those loops. That gives me the total amount of enclosed current. Box 9, there's my updated Ampere's law. BH equals mu naught times HNI. The H's cancel, and box number 10 gives you the expression representing the strength of the magnetic field at the center of a solenoid. It could be at any point along the central axis of that solenoid. So we just derived the magnetic field for a solenoid, and notice there's no dependency on geometry. As it says here, the cross-section geometry could be a circle, square, triangle, etc., as long as it's a solenoid. I'll conclude with this photograph of the world's largest solenoid. This is known as the compact muon solenoid. It's part of the Large Hadron Collider facility that's used to find fundamental particles. Maybe you've heard of the Higgs boson. This solenoid creates exceptionally strong and very precise magnetic fields, which are essential to the study of what happens when you blow up atoms and nuclei and subatomic particles.